Hello, my name is Groun and I'm a PhD student in la Universidad Politécnica de Madrid and part of the Model Flows group. Today I'll be presenting our work, which is titled Higher Order Dynamic Mode Decomposition from Fluid Dynamics to Heart Disease Analysis. Work has already been published in the Journal of Computers in Biology and Medicine, and since today's talk will be to summarize the work we have discussed in this paper. So for any further information, details, or concerns, you can turn to this paper, which I will be leaving the link to under the description. So the outline of today's presentation will be as follows. I will start first with the motivation behind our work, and next I will introduce the technique we have been using, which is higher order dynamic mode decomposition, or also called the HODMD. Next, I will introduce the material we have been using, which is the medical data, followed by the results we have obtained, and finally, I will close this presentation with some conclusions. So let's start first with the motivation. So the main motivation behind our work is fluid dynamics. As we all know, fluid dynamics play a central role in several applications in many fields, as we can find them in nature, in water, wind, or blood flow also. We can find them in energy production, such as in wind turbines, and of course in aerospace for aerodynamic shape optimization and for stability and control, and so on. So understanding these flows and controlling them will allow us to improve the performance of any system we want. So as soon as we talk about fluids, we must introduce the concept of patterns, because no matter how complex your system is, there will always be patterns or dominant features that define your fluid flow. And understanding these patterns will allow us to simplify the understanding of these flows, their nature, and their stabilities and instabilities. And by that, as I mentioned earlier, we will be able to control and also to improve any system we want. There are several techniques that have been introduced for pattern identification in fluid mechanics, but today we are focusing on the data-driven tool, which is called the Higher Order Dynamic Mode Decomposition, or HODMD. This technique is an extension of the well-known dynamic mode decomposition, and it was developed in 2017 by Soledad Leclange and José Manuel Vic. This tool is a data-driven tool which is introduced in the field of fluid mechanics for the analysis of complex data modeling non-linear dynamical systems. So how does this technique exactly work? So usually for data-driven tools, the data is arranged in a snapshot matrix. So we have snapshots of the state of our dynamical system in different time steps arranged in a matrix or a multidimensional array, which also can be a tensor. So each column of this is representing the state of our dynamical system in different time instants. So the main goal of the HODMD technique is to analyze the signal and to decompose it into an expansion of N modes or M modes. This mode has their own frequencies, growth rates, and amplitudes. In order to reconstruct this expansion, the HODMD technique takes two main steps. The first step is dimensionality reduction using the singular value decomposition, and it's mainly done for denoising. And the second step is the DMDD algorithm, and it's considered as a combination between standard DMD or classical DMD and Taken's delay embedded theorem. And in this step, the classical DMD is extended using the delayed snapshots. This was a short introduction to this technique, but the detailed explanation of the tool can be found in this paper, which I will also leave the link to under the description. So now we can move to the material or the medical data sets we have been using. So the data sets we have been using is echocardiography video loops taken from mice in different cardiac conditions. So these video loops are taken from the long axis view presented in the cut A and the short axis view presented in the cut B. These video loops has number between 120 to 300 snapshots per video sequence. And as I mentioned, they are taken from mice in different cardiac conditions, including mice in healthy conditions, mice in diabetic, obesity, heart attack, and hypertension. So the original images came in this form, in DICOM format, and we tend to crop the images to remove any medical information surrounding the image to make sure that it will not disturb the signal. So all the video sequences has gone through this procedure which is presented in this slide. So we take each video sequence and we extract the images. We crop them in order to remove any information that might disturb our signal. We convert the images into grayscale and arrange them in a multidimensional array. This tensor, which we'll call the snapshot tensor, will be the input of our HODMD technique. So the HODMD will analyze the tensor and decompose the signal into a set of DMD modes, where each mode has its own frequency, growth rate, and amplitude. And we believe that these DMD modes are representing the main patterns or the dominant patterns related to the different cardiac conditions. We can now move to the results we have. The first result we notice is the captured frequencies. As we can see here, the HODMD technique was able to analyze the signal and segregate it into two different lines of frequencies, where the upper branch is representing the heart rate and the lower branch is representing the respiratory rate. And we can see the same behavior for the short axis view data. And this behavior has been noticed through almost all different data sets we have analyzed. And we can also notice some segregation or some fluctuations in the frequencies between the heart rate and respiratory rate, but this is completely normal. And it goes to the reason of the different ages of the mice, as well as the gender, and also the dose of anesthesia the mice might have. The second result is the extracted features or the DMD modes, where we can see here when we compare the original images with the DMD modes, which we believe they represent the main patterns and features related to different cardiac conditions, we can see that these DMD modes are displaying more details and clear features and patterns when compared with the original images. And we believe these patterns will simplify the distinguish between the original images of the different cardiac conditions. So we can use these DMD modes and these features to classify, for example, different cardiac conditions in an easier way and more accuracy. So with this, we can reach the conclusions of this work. First of all, we can see the flexibility and the variety of the applications of the HODMD technique, as this tool was originally introduced in the fluid mechanics, but now has extended in different fields, including medicine. The second point is the ability of the HODMD to capture frequencies related to both the heart rate and the respiratory rates. And we can say this is a very strong point for the HODMD, as it needed only 120 images or snapshots to reach these results. And for the data-driven techniques, 200 or less than 200 snapshots is considered a very limited amount of data. And the last point is the utility of the HODMD technique as a pattern identification or feature extraction tool. As we've seen in the previous slide, the DMD modes, which we believe they represent the patterns and features related to the different cardiac condition, can be seen showing more details and clear features and patterns related to the different cardiac conditions. And this will allow us to distinguish between the different cardiac conditions in an easy way. All the codes related to this work or this contribution can be found in the website of the Model Flows app. This is also an open source software, so it is possible to download it and use it for different applications, where also can be found tutorials on how to use this software. This will be the end of our talk, so if you have any concerns or any questions, you can leave them in the comment section. Thank you.